In this video I'm going to just highlight what is the required work to be done on the ADCS system for MeznSat. Now the ADCS system needs some work. We need the ADCS team to push for the ADCS design, basic design issues in preparation for the PDR. Now in this video I'm going just to highlight the things that I would expect that the ADCS team will accomplish with just tiny basics. Maybe in the future when I have time I'm going to produce some more videos explaining the basics of some ADCS concepts if required by the ADCS team, but I would expect that this should be done by the team themselves. The AURAC ADCS team members, I'm going to carry a few tutorials with them in order to put them on track with ADCS design, ADCS basics. So here I'm going, as I said, we're going to look into what are the basic steps that I'm expecting from the ADCS team. So I would expect them to understand much of the background knowledge of ADCS design. The last thing we want is to have a question at PDR that is not being answered in a professional manner. So we need everybody to be acquainted with the ADCS concepts and have a good background on this. And everybody who needs training, please let me know. We're going to try to train them. So we need everybody to understand at least the basics of the ADCS design. We don't require you to go through the details of much of the equations that are related to ADCS, so it's not like we're doing a course on ADCS, but at least you should be able to design a complete ADCS system. So we're talking about system design basically, not about theoretical details of the system. So I would expect that you understand the background, to have background knowledge of the ADCS system. Also, you will be able to define the requirements definition. We have the requirements definition in MCR, but I think this has to be developed and tuned in a better manner. Then we have the core of the design, which is defining the concept of operation. And again, I said that we are actually looking for systems design instead of actually completely integrating a full ADCS system. So we want you to be able to design an ADCS system. So one of the main components of an ADCS system design is the definition of the concept of operation of the ADCS system, as we're going to see in a bit, and then to carry out the analysis and simulations. So luckily we have both a very powerful simulation tool that can be used for this. It's very simple to use, so things should be very easy. So these are the steps that we require: background knowledge, requirements definition, define concept of operation, and the simulations of the ADCS system. Later on, of course, we will add a few other things like hardware in the loop simulations, but now this is what I'm talking about. This is what is required for the PDR. So let's go to the first step here, step number 1, background knowledge. So background knowledge, there are 4 components that you need to understand briefly. Kinematics, ADCS kinematics, related kinematics, which is basically the orientation, let's say, orientation details of the spacecraft in space, because if you want to design a control algorithm, you need to define how is it oriented in space. Then you have attitude estimation algorithms. So this is a complete topic on its own. So you have different attitude sensors coming from different places, like sun sensor, you have star tracker, magnetometers. These are reference sensors, and you have rate sensors like the gyroscope, accelerometers. Some of these are actually available at different times, and data from them are not available at other times. So these algorithms actually do the complete attitude estimation of the spacecraft, given the error that is available from the data coming from these sensors. So this is a complete field. One of the important algorithms here is Kalman filter. So Kalman filtering is an important algorithm that needs to be understood. So actually this is a complete area of study. So the most important of these all is basically the control algorithm. So you need to understand the basic control algorithms that could be used with the ADCS system. So as control engineers, this is one of the primary things you need to be understanding, to understand what are these, and all of these are actually, you can say that they might be derivatives, or let's say if you understand the PID controller, you can understand lots of these other algorithms. So there are some famous algorithms that we're going to see, like the B dot algorithm, and other algorithms that are used for the control, magnetic control, and also motor control. So these control algorithms, how are they designed, what are their basics? So this is something that you need to understand. Sensors and actuators, the hardware part. You need to understand what are the hardware components, of course. These are very basic. So compared to the others, this is really very basic knowledge. So you need to understand what is a star tracker, sun sensor, GPS, horizon sensor, magnetometer, what do they do, what's the advantages and disadvantages of each. Star tracker, for example, has very high accuracy, however it is very expensive in several terms. In terms of power, in terms of money. On the other side, you have a horizon sensor, which is a good middle way sensor, and you have some other sensors. So what I mean is that you need to understand what is the possible hardware to be included in any ADCS system. So this is really the basics that you need to go through and understand. Luckily for you, we have actually chosen already the ADCS that we are going to use after actually having a study of several ADCS components. We have chosen Cube ADCS, which is something developed by, which is an ADCS integrated ADCS system designed by a South African company, which is a spin-off of a university over there in South Africa. Of course, there are lots of advantages of using this Cube ADCS. One of them is actually cost. So this is really cheap one compared to the other American alternatives, and again, it's very reliable. The QB50 satellites, all of them, I would say, have used this as this ADCS system with different configurations, of course, for each. Some of them are using reaction wheels, some of them are not using reaction wheels, different sensor configurations, but all of them are actually using this. So it's actually a reliable ADCS system, and it comes with really very good support. So it's actually a good choice, I believe. Here in this figure, you can see we have horizon sensor, we have sun sensor, we have magnetic torquers, and then we have the reaction wheels. And you can see a stack of boards here that we're going to look into. Some of these are computers and some other stuff. So this is actually the way it actually looks generally. More information on this, so lots of details, which is basically a very good starting point for you to look at, is the user manual, which is available on Google Drive. You will see it. This is actually a very useful document, and I think this is a very good starting point for you to look at and understand the details of the Cube ADCS. Here you can see lots of details as you scroll down, and I'm taking actually lots of the slides from this document itself, so this is a very good starting point. Okay, so back to this. So what the Cube ADCS system actually consists of, it's actually a stack of a few components. So CubeStar, which is the star camera used, then Cube Connect, which is an interface board to the reaction wheels. So we have three reaction wheels used here. Reaction wheel is actually a motor used for controlling controlling the attitude of the sensor, and we have three of the spacecraft, and we have three of them, one for each axis. Then we have Cube Control, which is basically the computer. No, sorry, this is actually the driver. So this is the interface board for some of the sensors and actuators. So this is the magnetic torquer. Here you have the rate sensor, and we have the magnetometer. All of this is connected to Cube Control. A CubeSense is the board that has the sun sensor and the nadir sensor, each one pointing on one side of the spacecraft. So if this is the sun sensor here, this will be the nadir sensor on the other side. Then we have the Cube Coil, which is used for Z-axis control, X-axis control of the spacecraft. So here, because we have two torquers here, one on the Y-axis and one on the Z-axis, then we have the Cube Coil to control the X-axis. Finally, you have the Cube Computer, which is basically where your control algorithm runs. This could also be used as an OBC, but let's not talk about this now. So this is used to control the ADCS system. So we have also 10 coarse sun sensors that has to be appropriately placed on the spacecraft, and this is connected to cube control. All of these details are in the document, so I would advise that you actually look into this and study the ICD from the Cube ADCS document user manual. So more on this. So here you have the cube control, cube sense with the sun sensor and the another sensor, the cube computer, which is basically the computer that runs the control algorithm. We have 3 cube wheels, and we have the star tracker here, the star camera. So you can see the details here. So all of this is actually from the user manual. So this is about the basics, background. So this is what we need you to understand in terms of background. So now we need to move on to the requirements part, which is basically very important. So once you understand the background necessary, you can define the requirements. I've taken a sample requirement from QB50 documents, and you can see some of the requirements that are defined here. The CubeSat shall be able to recover from tip-off rates of up to 50 degrees per second within 3 days, nominal conditions. And then you have the science unit will be accommodated at one end of this CubeSat on a 10 millimeter face. So here you have some of the sample requirements from QB50. So I would actually refer you to QB50 to understand many of the concepts behind ADCS. They have very good documentation. I've taken this from another document before I forget, let me just talk about what we have on the Google Drive folder. So in the Google Drive folder, I have included a reference page under MeznSat team. You can see references. Under references, you have ADCS, and here I have included many documents that could form your reference for background information on ADCS, including QB50 information, cube support, and the ICD. Also, I've included a folder which is recommended first reading. So I would actually recommend you to go through these 3 documents. The first one of these is a document that is well written. Basically, it's a report from Aalborg University, and it explains the design of AEUSat CubeSat, and it's actually very well written and has lots of background information that you can look at. B.controller, here you have the controller design, and then most importantly you have some background information. So that's actually a really very good document. So I would recommend that you start with this document. So back to the requirements. So we need to review the requirements. So these are sample requirements. This is a requirement that is derived from the payload requirements, field of view requirements. So you have some equations here, and this is again a snapshot taken from this document here, from the Aalborg University thesis. Okay, so requirements is the next step. So the third step would be actually to go through the ADCS concept of operations. So here I mentioned that the first thing that you need to do is the background knowledge, then requirements definition, and then we need to define the concept of operations. So what basically the concept of operations is what are the modes, what does the ADCS system do during the lifetime of the mission. And this is not to be confused with the with the CubeSat's main concept of operations that has been prepared previously, and I showed it in one of the videos. And it's there on the online documentation. So this is a different thing. This is the concept of operations for the ADCS itself, and this of course has to be. So the ADCS team has to design the ADCS concept of operations. What are the modes that the ADCS is actually going through, and link this actually to the main concept of operations modes of the spacecraft itself. So there has to be a link between both. This should be done by the ADCS team and also the systems team together. But let's start with having the ADCS team understanding what is their concept of operations first. So to give you an understanding on what this will look like, so basically what we are looking for is actually what is ADCS going to do during its lifetime. So it's natural that the first thing that the ADCS will do is to detumble the spacecraft, because directly after launch, the spacecraft will be tumbling at a high rate. You can say between 5 to 10 degrees at each axis. You can say that this is a worst case scenario, but we have seen missions that actually are tumbling at a higher rate, let's say even 6 times this speed, so maybe 60 degrees per second. But the expected one is around 55 to 10 degrees per second. So the ADCS has to detumble it down and stabilize it to less than, let's say, 0.5 degrees, let's say, per second, even less than that, but that's something that you figure it out. Then we have controlled spin mode. So now we are actually moving from uncontrolled system to a controlled system. Then we have high pointing requirement mode, which is basically 3-axis pointing. So if you're taking an image, you can go to this mode. So this is generally an idea. So I'm not actually saying that this is what has to be done, but these are 3 very common modes that are actually usually there in most satellites. So this is something that will give you actually what are the modes that could be involved in the ADCS concept of operations. So detumbling, control spin, and high accuracy pointing. So this is taken from the QB50 document, also from CubeSpace documentation. So this is an example of what happens in the detumbling control mode. You have motion that is taking place in one axis. So you have the detumbling has actually controlled the spacecraft on 2 axes, the X and Z axis, while you still have the Y axis being you are having movement on the Y axis. As you can see, you have it oscillating here in this way. And then the suggestion from the QB50 and from CubeSpace is to turn on the Y-axis reaction wheel. So they have only one reaction wheel in most of the QB50 missions, while we actually have 3. So here they have one reaction wheel that controls the Y-axis. So this is after detumbling. Then you move on to the Y momentum mode, which actually puts the pitch to 0. So it puts the Y-axis movement to 0. So this completely stabilizes the spacecraft on all 3 axes. So this is an example of the modes and what each mode is actually doing. So the ADCS concept of operations will have to actually define what is the ADCS going to do step by step throughout the lifetime of the spacecraft. So this is a typical concept of operation flow chart. So here you have the state diagram, ADCS state diagram. This is taken from QB50, starting from idle, then estimation mode, and then detumbling mode, and then moving on to the Y Thomson tumbling steady state, and then Y momentum state. So all of these states has some actions taken by the ADCS system. So this is also taken from the CubeSpace documentation. So these are the possible estimation modes from CubeADCS. So depending on what command you give it, so it will actually change the estimation mode. So this is something you need to understand. What are the difference between these different estimation mode? So you have the extended Kalman, full state extended Kalman filter. This is the full state filtering, top performance, and then things are actually varying in accuracy. So here you have MEMS rate sensing, different types of actually estimation modes that I would actually invite all of the ADCS team to understand what each of these modes are actually referring to. Let's move to control system. Before we go into the control modes, I want to say one thing, that the control algorithm will be running on the Cube computer, and you can see that your control program will be running here. Now in this mission we will not design the control algorithm, so we will be looking into systems level design basically, and this is the current plan. Let me say maybe things will change in the future, but now this is the current plan, is actually to look into the ADCS design and on the systems level. So we don't have to go at this stage for this mission into the details of implementing the control program, they will be already programmed and by the by CubeSpace. But we need to define what are they, how do they actually work and when do they work. So this is called systems design. So these are the control algorithms that are defined by CubeSpace in the Cube ADCS. So you have no control, detumbling control, Y Thomson spin, Y momentum wheel, steady state, and initial pitch. Then you have XYZ 3-axis control, which is actually a very accurate pointing accurate mode. Details of this is actually explained in the manual itself, so you can see what each of these stages are actually doing. Detumbling, Y momentum control, and inside the detumbling stage you can see that we have 4 control modes: B dot detumbling, Y Thomson. So you need to understand what there's no scope. Explaining all of this is beyond the scope of this video, but what we need you to understand carefully is what are actually the details of each of these control algorithms and control modes. This is your task as an ADCS team. One more thing is to see now these are the control modes available and what are the corresponding estimation modes. So here, for example, if you're going through detumbling, then all of these are possible estimation modes that you can use: magnetometer rate, triad, MEMS rate, but you can see that you cannot use a full state Kalman filter, extended Kalman filter, which is different in the Y momentum and XYZ wheel mode. So here you can use extended Kalman filter. So this is actually a valid estimation and control combinations that is also from CubeSpace documentation. Okay. An important decision to make is the orientation of the ADCS components within the spacecraft structure. So here we have a few issues that we need to resolve. Currently the systems team is dealing with this. So one of the things that we currently are studying is the orientation of the sun and the nadir sensor along with the star tracker. We can notice here that the magnetometer is a deployable magnetometer and it's on the structure on the outside. One thing to notice is, I mentioned this in a previous video, is the positioning of the sun sensor. So previously we were putting it, because it was an ISS orbit, we were having the nadir sensor with the lenses of the Argos and the RGB camera pointing downwards to Earth, while the sun sensor points upwards, because this is the way it is designed. It is designed to be in the opposite direction of the nadir sensor. However, now that we are moving to probably into a sun-synchronous orbit, where in the sun-synchronous orbit, this is the sun and this is our orbit, and you will see that basically our sun sensor will have to be pointing in this direction. So it is not in the direction opposite to nadir, it will be on the side 90 degrees from nadir. So it will be on the side here, so throughout the orbital lifetime of the spacecraft. So that means that the orientation will have to be flipped for the nadir sensor and for the sun sensor, so they will have to look into this side 90 degrees from the nadir, where the Argus and the RGB camera are pointing towards nadir. Star tracker. So another thing to study is the star tracker positioning. I don't want to go into much details here. I'll leave it to the ADCS team to study this further. So, but just now we are left with two options with the star tracker, either to point it opposite to nadir, or to point it opposite to the sun sensor's direction. So I would invite the ADCS team to study this in details, please. Okay, so now it's time to move on to the EOS software and to the simulation part. So I mentioned that this is actually the last thing I require from the ADCS team is to complete the simulations. So background knowledge, requirements definition, define the concept of operations, and finally the simulations of the ADCS. So for the simulations, we actually acquired the software from CubeSpace to do the simulations. If this software was not available, we would have to have done it in Simulink. But luckily enough, CubeSpace will make our life much easier, and they are providing us with the software. So I have to say that this software is actually available on the Google Drive. So the folder is actually inside the simulation folder. Zip folder is on on the Google site. The way you can access it is from the files, and then if you go to downloads, it will open Google Drive for you, and under ADCS you will find that it's actually EOS version 1.1. This is an updated version of the previous copy. So this is a zip file that you need to download. Once you download and unzip, this is what you get. So you want to launch it, you double click on the exe file and it will be started. So this is the window that you have. And just a quick demo, I want you to actually, the ADCS team has to actually look into all of the features of this powerful simulation tool. But to keep you going, so I will just demonstrate a quick thing. So if we start by actually setting up a scenario, a simulation scenario, so let's say now we want to start detumbling, so with an initial rate, let's say 5 degrees, and then here we have on the y-axis -7 degrees per second, and then on this axis let's go really bad and go say we'll have 10 degrees per second. And now let's check up on, so here you can see actually the configuration of the satellite. So here you have the simulation model, and then here we have the hardware in the loop model, and this will be used later on when we have the hardware here in the UAE. We can actually start playing with this, but now let's focus on the simulation model. And you can see the configuration of the satellite. If we look into the details here, you can see that you can actually select the control mode. So let's actually go for magnetic stabilization using B dot, and then maybe we go for magnetometer rate Kalman filter. So here I want the ADCS team to actually play around with this and see what's the different combination, what are the different combinations possible, and what are the results that are yielded by each control mode. So this is what we need to figure out basically from the simulation tool. So here we are using magnetic stabilization to detumble as an example. So here then I will move on to the simulation environment, and here you can see the satellite. I will actually go for MeznSat here, and then I will actually see it running, and here you can see it running, tumbling really quickly. So you can see it tumbling, and hopefully it will detumble and reduce its speed. It's using the magnetic controller, so it's actually, it has successfully reduced its speed. It did not put it into a halt, but this is what is actually expected from the B dot controller. Now you can see if you can actually move if you want to move to a higher control. Let's actually try to do it. And if we change the controller to, let's say, 3-axis controller, so we go to the model and then we move on to 3-axis controller. Let's move to XYZ wheels, so use the magnetic torquers, and then we have EKF, extended Kalman filter full state, and see if we actually have if we have a quicker detumble. So let's run the simulation and see. So you can see here we have a different behavior and it doesn't seem to work. So let's go back and change the let us change the control mode, and we just go for, we'll keep the control mode, and then we'll change the Kalman filter here. So we'll move on to the reference satellite, reset the simulation, run the simulation, and we can see that here we have a better performance. You can see that it's actually nicely stabilized. So still there's movement, but I mean, this is what we need to actually look into the simulation details and see how actually this is going to work with our control algorithms and attitude estimation algorithms. Now finally I want to move on into recording the results. So if I want to, let me go back and see, actually let's actually see how to record the results. So if you go down here, so if I move on to the satellite kinematics, let's say that I want to record the attitude of the satellite during the simulation period. Here you can see that we have orbital angular rate. If I run the simulation, you can see it actually diverges. It's tumbling, and then at the end it actually stabilizes here. So you can see that very clearly. So let me reset it again and then run it once again. So you can see that it's actually it's tumbling, and then it actually stabilizes quickly. Say that you want to record the results, so what you do, so let me actually, in order to avoid the computer from crashing, so let me stop it and then export it to a CSV file, EOS. I'll call the file EOS test1, and then I will save it. So I have exported the simulation of the orbit body angular rate, and I will open it with Microsoft Excel. And here we can see actually the results of the simulation, and this data can be used. So here you can see that the speed is 5, 6.5 and around 10 as we set the initial tumbling rate, and you can see that it actually quickly stabilizes. It actually stabilizes to less than 1 degree per second. So you can see the results here, and these results can be recorded and can be done in a graph, and it can be actually exported to whatever software you need. So that's a good advantage. Okay, so I think this brings this video to an end. So as I want to remind everybody that we would like to have an initial output from the ADCS team at around April 7th, please. So that's the plan, and I will discuss with the ADCS team separately. So let us hope that we can get some results from all of you guys by April 7th. So thank you very much for listening, and I'll talk to you soon.